Today we're going to discuss some basic ideas involving matrices. And the first thing I have to do is tell you what a matrix is. A matrix is an array of numbers. So here we have such a matrix. It has 2 rows, and it has 1, 2, 3 columns. So there are 3 entries in each row, and there are 2 entries in each column. Entries are named by the row and column they occupy. So for instance, 4 here is in the first row and the 1, 2, third column. So we call it A13, where this subscript tells you what row it's in, and this subscript tells you what column it's in. So we will often write capital A is parens little aij, where these are the entries in the matrix. Okay, so this entry is the 1, 1 entry. This is the 1, 2 entry. This is the 2, 1 entry, second row, first column. And you can see here that a 2, 2 is 2, and a 2, 1, second row, first column, is 3. Here's a matrix B. This is called a 2 by 2 matrix. It has 2 rows and 2 columns. B21 is second row, first column, 7. B12, first row, second column, 1. Just a note before we proceed: one matrix, several matrices. So matrix is the singular, matrices is the plural. Okay, now let's talk about operations that you can do with matrices, and one of them is addition and in fact subtraction. I'm just going to show you addition. I think you can probably figure out subtraction from this. Okay, so you take this matrix which has 2 rows and 3 columns, and you can add it to another matrix if that matrix has 2 rows and 3 columns. And the way you add is just component by component. So the 1, 1 entry in the sum is going to be 3 from the 1, 1 entry in the first matrix, plus minus 1 from the 1, 1 entry in the second matrix, and we get 3 minus 1, or 2, which is the entry that we get in the sum. And then we just go along. 1 plus 2 is 3, 2 plus 0 is 2, etc. And when you add together 2 by 3 matrices, you get a 2 by 3 matrix, where each entry in the sum is just the sum of the entries from each of the 2 matrices. Now notice that the matrices must be the same size. We cannot add a 2 by 3 to a 2 by 2 because the coordinates do not match up, and there's no clear answer. So if the matrices are not the same size, you can't add them. Now another thing you can do is you can take a matrix and you can multiply it by a scalar. Here we're multiplying 4 times our 2 by 3 matrix, and the way you do it is just 4 multiplies every entry in the matrix. So 4 times 1, 4 times 2, 4 times 0, 4 times 1, 4 times 4 gives us the matrix 12, 4, 8, 0, 4, 16. Now, the last operation, which is much more complicated, is matrix multiplication. And the matrices don't have to be the same size, but they have to be compatible, and we'll see what that means in a bit. So here A is a 2 by 2 matrix, B is a 2 by 3 matrix, and it turns out that A times B is defined, but B times A is not. We multiply A and B together to get C, as follows. The 1, 1 entry in C is going to be the dot product of the first row of A with the first column of B. So we think of that first row as a vector with 2 components. We think of this first column as a vector with 2 components, and we dot the 2 of them. So we get 1 times 3 plus 2 times 0, and that's the first component in C. And that emphasize that again. Calculating products of matrices involves dotting rows of the first matrix with columns of the second matrix. So to continue, if we want the 1, 2 entry in C, the product, we're going to take the 1 first row of A and dot it with 2, the second column of B, and we're going to get 1 times 1 plus 2 times 1, and that gives you the 1, 2 entry here, first row, second column. Now for the 1, 3 entry here, first row, third column, and you're going to get 1 times 2 plus 2 times 4, and that's this entry. Now to get the 2, 1 entry in the product matrix, we dot the second row over here, row 2, with column 1, and we get minus 1 times 3 plus 1 times 0, and that's the 2, 1 entry. And now to finish here, we need the 2, 2 entry, and that's the second row dotted with the second column, minus 1 times 1 plus 1 times 1, and finally the second row dotted with the third column gives us minus 1 times 2 plus 1 times 4, and we have finally the matrix 3, 3, 10 minus 3, 0, 2, which is the product. Now let's consider the product B times A, where B is our 2 by 3 matrix and A is our 2 by 2 matrix. When we attempt to dot the first row of B with the first column of A, we see that's not possible because they don't have the same number of components. So this matrix product is actually not defined. And if you look at what the problem is, there are 3 entries here, 1, 2, 3 columns. There are 2 entries here, 1, 2 rows. This isn't going to work unless the number of columns in the first matrix is the same as the number of rows in the second matrix. So if you've got an M by N matrix and you're going to try and multiply it by an R by S matrix, A times B is only going to be defined when N, the number of columns of A, is the same as R, the number of rows in B. Okay, and if you have an M by N matrix and you multiply it by an N by R matrix, you're going to end up with an M by R matrix. Okay, and we saw that before when we multiplied a 3 by 2 times a 2 by 2, we ended up with a 3 by 2. The number of rows in A and the number of columns in B. So a 2 by 3 times a 3 by 4 will produce a 2 by 4. Now, matrix multiplication has some really nice properties. So in what I'm about to talk about, assume that all the operations below are defined. In other words, if we're adding 2 matrices together, they're the same size. And if we're multiplying 2 matrices, the matrices are compatible, which means the number of columns in the first matrix is equal to the number of rows in the second matrix. matrix. Okay, so assuming all that's true, A times B plus C is AB plus AC. This should look like a fairly familiar property, and in fact, if a scalar multiplies the matrix B, A times RB, the scalar just slides out in front, and it's RAB. And if we combine these two, we're going to see that A times RB plus SC is RAB plus SAC, which ought to look very familiar. Okay, multiplication by A is linear, and we could actually think of A as a linear operator. And this is going to turn out to be important because we're going to be looking at linear equations using these ideas. Now, one of the things that we will be working with a lot is a square matrix. In fact, any matrix that's n by n is called a square matrix. And a lot of the matrices that will appear in problems are going to be square, and we're going to need some techniques to deal with them. Now, a nice thing about square matrices, if A and B are square, n by n, then you can take the product of AB or BA, and you end up with an n by n matrix. Now, a property that is important about an n by n matrix is that it has a determinant. And we denote this either by sort of absolute A or det parens A. Now, you have some familiarity with this already. If A is a 2 by 2 matrix, A, B, C, D, then the determinant of A is AD minus BC. For 3 by 3 matrices, we know how to expand a 3 by 3 around the first row, and one can always do that, but it turns out that you can expand around any row or any column using the following plus or minus grid, which you'll see is plus minus, plus minus, plus minus, etc. An entry is positive if the sum of the row number and the column number is even. So for instance, this is 2, 2. 2 plus 2 is 4, so it's plus. And it's negative if the sum is odd. So this one is 3, 2. 3 plus 2 is 5, so it's negative, and that's going to tell us whether the little 2 by 2 we get is going to have a plus in front of it or a minus. Let's do an example. Now, what you're used to doing is expanding around the first row of the matrix, but what we're going to do here is expand around the second column of that same matrix, and here's what we get. So we look at 1 and notice that it's in a negative position because this is first row, second column. 1 plus 2 is 3, so that's going to count as a minus 1. Okay, and then what we're going to do is not include anything in that column and in the row the 1 is in, and what we're left with is a little 2 by 2, which is 1 minus 1, 1, 1. So we end up with, for that term, minus 1, which is this one, times that little 2 by 2. Now when we move down to here, we see that 0 is in the second row and second column, so it would go as a plus. However, it's a 0. So the fact that our little 2 by 2, 3, 2, 1, 1 is what goes here is not too important. And now finally we look at the third entry in this column, and we don't include anything in that row and this column, and that gives us a 3, 2, 1, minus 1 as our little 2 by 2. This is in a negative position because it's third row, second column, which is 5, so negative. So we've got a minus 1 times our little 2 by 2. And now we just evaluate this. This is 1 minus minus 1 or plus 1. 0 times who cares. And 1 times minus 3 minus 2, which gives us minus 2 plus 5, which is 3. Now, how do we evaluate a 4 by 4? Well, it's the same idea, except after we do it, we're going to get 3 by 3s, and then we're going to have to do it again. However, for this particular problem here, you can see that there's a good choice you can make about how to expand. This column has all zeros in it except for 1, 1, which means the expansion is really going to be easy. So what we do here is that's going to get us a 0 times a 3 by 3. That's going to get us a 0 times a 3 by 3. This is the only thing that gets us anything. Okay, and we'll note the 1 is in third row, second column, negative position. So that's going to count as a minus 1. And now we look at the little 3 by 3 we get, which is 1, 2, 4, minus 1, 2, 1, 0, 5, 1. And now what we have to do is calculate the 3 by 3. And what we're going to do here is we're going to use the third row, and the idea being there's a 0 here. I might just as well use the first column, but the third row just for practice. And we get a 0 from this guy. 5 is in an odd position, third row, second column, 5. So we get a minus 5. And now the little 2 by 2 that we end up with is 1, 4, minus 1, 1. And then finally, we're going to expand around the 1. And we get this little determinant 1, 2, minus 1, minus, or 1, 2, minus 1, 2. And this 1 is in a positive position because it's row 3, column 3. So that counts as a plus 1 times our little 2 by 2. And now we just evaluate these things. This thing is 1 minus minus 4, which is 1 plus 4. This thing is 1 times 2 minus minus 2 is 2. So we're ending up with a minus 25 plus 4, which is minus 21, times minus 1, which gives us 21.